Welcome back. Have you ever stopped and wondered how the device you're watching this on right now actually thinks? Well, it all boils down to something incredibly simple but super powerful: logic gates. They are the secret language of literally every digital device. So come on, let's learn how to speak it.
I mean, really, how does a calculator know that 1 plus 1 equals 2? How does your phone know to unlock with the right passcode? You might think it's some kind of complex magic, but the answer is actually built from millions, even billions, of tiny electronic switches, all making basic yes or no decisions at an insane speed.
And that's our starting point, the digital decision makers. We're about to meet the fundamental components, the absolute bedrock that makes all of this digital wizardry possible.
So what is a logic gate? At its core, it's just a tiny decision maker. That's it. It takes in one or more little pulses of electricity, which we call inputs, and these are always either a 0 for off or a 1 for on. Then, based on a very simple rule, it spits out a single output, which is, you guessed it, also a 0 or a 1. They are quite literally the Lego bricks of every digital circuit in existence.
Okay, so in this section, let's meet the main characters of our story, the basic gates. There are 3 really fundamental types that form the basis for pretty much everything else, and we're going to start with the simplest one of them all.
First up, we have the NOT gate. I like to call this one the rebel, because its only job is to do the exact opposite of whatever you tell it. It's got just one input and one output. You feed it a 1, it spits out a 0. You feed it a 0, it gives you back a 1. That's the whole deal. Simple, right?
And here's what it looks like in a diagram. This is how engineers draw it. That triangle with the little circle on the end is the universal symbol for inversion, for flipping the signal. So anytime you see this in a circuit diagram, you know, that's a NOT gate. That's the rebel.
Now, this little chart here is called a truth table. Just think of it like a cheat sheet that tells you exactly what the gate will do. And for the NOT gate, it's about as simple as it gets. If input A is 0, the output is 1. If input A is 1, the output is 0. That's the entire rule book for this little guy. All right, let's meet our second gate, the AND gate. This one is the strict one. It has 2 or more inputs, but here's the catch. It will only, and I mean only, output a 1 if every single one of its inputs is also a 1. If even one of those inputs is a 0, the output is 0. No exceptions, no excuses.
The symbol for the AND gate is this very distinct D shape. You see that? The flat back, the curved front. When you see that shape, you know you're looking at a strict AND gate that's demanding that all conditions are met before it lets a signal pass.
And its truth table really tells the story. Look at that output column. It's almost all zeros. The only time we get a 1, the only time it says yes, is that very last row, where input A and input B are both 1. In every other situation, it's a hard no. It's all or nothing with this gate.
And now for our third basic gate, the OR gate. I call this one the easygoing one. Unlike its strict friend, the AND gate, the OR gate is way more flexible. It'll output a 1 if input A is 1, or if input B is 1, or if they're both 1. It's much more accommodating.
Its symbol is curved too, but notice the difference. The back is also curved, kind of like the tip of a shield or a spaceship. This unique shape is what sets it apart from the flat-backed AND gate. It's a visual clue that its logic is more inclusive.
And a truth table totally reflects this easygoing personality. Look at this. The only way you can possibly get a 0 out of an OR gate is if all the inputs are 0. In every other case, as long as there's at least one little 1 coming in, the output will be a 1.
So we've got our 3 basic gates: the rebel NOT, the strict AND, and the easygoing OR. Now you'd probably think you need all 3 of them to build something complicated, right? Well, this is where the story takes a really fascinating turn.
Believe it or not, and this is one of the coolest facts in computer science, you can build every single logical operation. You could build an entire computer processor using just one type of gate, just repeated over and over and over again. So, how is that even possible?
The answer lies in something we call universal gates. The 2 most famous are the NAND gate, which is just a combination of NOT and the NOR gate, which is a NOT-OR. They're like the Swiss Army knives of digital logic. Because you can arrange them to mimic any other gate, they're incredibly efficient for manufacturing chips.
Let's just prove it right here. Look at this circuit. We've got 2 NAND gates. The first one does its thing, but look closely at the second one. See how both of its inputs are tied together? Well, when you do that to a NAND gate, it behaves just like a NOT gate. So what we have is a NAND followed by a NOT.
The not part basically cancels out the N in NAND, leaving you with a perfect AND gate. It's like digital alchemy. Just amazing.
Okay, so now that we know the players, what can we actually build with them? Well, it turns out we can combine them to perform one of the most fundamental jobs of any computer, doing math. That's right. By just cleverly arranging these simple little decision makers, we can build a circuit that actually adds numbers together. The most basic version is called a half adder, and it's a foundational concept for understanding how a CPU, the brain of a computer, really works. Okay, check this out. This is a circuit called a half adder. On the left is the truth table that shows the rules for adding 2 single bits. And on the right, you can see how we build it. It uses an AND gate, which we already know, for the carry output. And for the sum, it uses something called an XOR gate, or exclusive OR. All that means is it only outputs a 1 if one input is true, but not both. And that's exactly how 1 plus 1 in binary gives you a sum of 0 and a carry of 1. It works! We just made a circuit that can do math.
So for our last section, let's zoom out. We've gone from a single gate to a tiny circuit that can add 2 bits. But the real magic, the part that's truly mind-blowing, is what happens when you scale this simple idea up to an almost unimaginable degree.
Every single thing your computer does, from rendering the beautiful graphics in a video game to processing huge amounts of data for artificial intelligence, it's all just the result of billions of these simple not, and OR gates, all making yes or no decisions billions of times every single second. It's just staggering complexity, all built from the simplest possible rules.
So the most important thing to take away from all this is that the entire digital world we live in is built on these few incredibly simple, logical rules. They're like the alphabet of computation. And that leaves us with one really fascinating question. Now that you know the basic rules of digital thought, what would you build?